So today we want to talk about now the first serious topic after the introduction is materials. And the first question is, why do we need to study the materials? Why material behavior is so important? In fact, right now in the analysis, structural analysis and modeling, the most difficult part currently is material modeling. We can model many things, but not materials correctly, and I will show you why. You might think, what is the problem with material? I just need E, modulus of elasticity is enough. But that is not the case, absolutely not the case. First of all, we saw the slide, first lecture, excitation, let's say load, structure, response. So how are they related? What is the relationship between that and that? The relationship typically is like this. It's like a spring. Structure is like a spring, like a big spring. You put loads on it, it deforms. And between the deformation of the structure, there is stiffness. So if you apply the load to the structure will deform, and the deformation U is proportional to the load, and the constant of proportionality is stiffness, K, correct? So it's like a spring. You take a spring, you put a load on it, it goes down, and the deformation in the spring is related to constant, the spring constant or the spring's stiffness, correct? So it should be very simple. So we shouldn't have any problem because it's right there. Force and deformation related by stiffness. So if we know the stiffness, we can always calculate the deformation for a structure, right? But not right. It's not that simple. What is the problem here? Can somebody tell me before we go on? What is the problem? This is what we mostly understand. This is what we do. We calculate the deformations from load to deformation by some form of stiffness, right? But what is the problem in this equation? The problem here is that stiffness definition, although is give a good definition, but next step is how do you calculate that stiffness? What is it? So what is stiffness? Its definition is absolutely correct. This is the resistance to deformation, right? Many people confuse stiffness with strength. That is not the case. And stiffness has an opposite. What is that? Flexibility. Flexibility is the ease of deformation. So 1 over K or 1 over stiffness is flexibility. So that means the structure which has small stiffness has high flexibility, large stiffness, small flexibility, right? So flexibility and stiffness are two sides of the same coin, opposite to each other, right? Now the question is, if we want to do the analysis, we need stiffness. How do we calculate stiffness? From where will it come from? That is what we are going to talk about. So stiffness, what is stiffness made of? Stiffness is actually made of many components, like this. Please watch this slide carefully. Stiffness is made up of, first of all, material stiffness, starting point. Then the material itself has no meaning. A block of rock has no meaning. You need to convert that into a structure. So the structural member must have a cross section. So cross section has a geometry. So there is going to be a geometrical stiffness of the cross section shape. And then you combine that with the material stiffness, becomes cross section stiffness. So the geometrical stiffness combined by the material inside that section. For example, there is a rectangular shape. That shape has no structural meaning, it's just a shape with an area. But if I combine that area with modulus of elasticity of the material that it is made from, it becomes stiffness. It becomes a structural material. So area of that rectangle multiplied by the modulus of elasticity, which is the material stiffness, I multiply them together, it becomes cross-section stiffness, EA. And then the axial load is related to the area of cross-section multiplied by E, and that becomes the stiffness of the cross-section. So the material stiffness is E, which is the resistance to strain right? For stress. Stress versus strain, E. So that becomes material stiffness. You take the material stiffness, you combine it with the area or the cross-section stiffness, geometric stiffness, you make it into cross-section stiffness. Then cross-section is one cross-section. If I have a long beam, then the length will become another factor. Longer the length, smaller the stiffness. Shorter the length, higher the stiffness of the member. So then the member stiffness, which will be made up from the member dimensions and shape. Arch, different stiffness. Straight member, different stiffness. Cable, different. So geometry of the member plus the size of this member combined with the cross-section, combined with the material, becomes member stiffness. Then that is one member. If I put many members together, it becomes a structure, and the number of members and the way they are arranged becomes structure stiffness. So progressively, from one step to next step to next step to next step, we are adding the structure. And finally, the stiffness of structure is a collection or summation of the material stiffness, cross-section geometry, member dimensions, member stiffness, and then number of members and structure stiffness. So that is the overall, that's how the structure stiffness is defined, right? So today our job is to start with the materials, and then we will go to next things step by step until we can reach the structure stiffness. So let's talk about material stiffness. So what is material, and what is the stiffness of a material, right? So this is the explanation for you to read what I just said. Now come back to the slide again. You remember this slide? And we said that there are two ways that we can go and talk about the structural analysis and design. One is to go this way, load to analysis. So between load and analysis is stiffness, right? So stiffness will relate the loads to the response. And on the other hand, if we use the other way, then material response will depend on the material stiffness, the right way. So either way, wherever we start, material stiffness will be the first thing that we need to deal with. Either we go from loads to actions, or we go from material to actions. Either way, material definition, material properties, material stiffness is the first thing that we will need to deal with, right? So let's talk about that. And now, same slide, if you remember this one, we said that actions to deformation depends on K, and strain to stress depends on material stiffness, right? You can call it E or whatever you want to call it. So that means the stiffness is the basis of all of that process. The first thing that you need, you cannot move between stress and strain without knowing the material stiffness. You cannot move between action and deformation without knowing the structure stiffness or member stiffness, right? So now we are going to take this way. So let's see what do we need to go from here to here, from strain to stress or stress to strain, either way. Let's talk about materials. We are not going to talk about other materials. We are going to talk about structural materials. So what does it mean, structural material? By structural materials, we mean materials for which mechanical properties are usually needed or known or defined so that they can be used for the purpose of analysis or design. So we need mechanical properties of the material. So if we are dealing with the mechanical properties of a material, that becomes a structural material, right? So for example, cement is a material, but we are not concerned about cement. We are concerned about concrete, which is made from cement, aggregate, water, whatever. That's the structural material. Cement is not a structural material, right? But concrete is a structural material. So that's how we will differentiate. The final material for which the properties we are going to use, that is going to be our structural material. It is showing you the hierarchy of how the material is organized. Basically, it's a material. Material can be divided into concrete, metal, non-metal, composite. So these are the main categories, right, of the materials. And then from concrete, we can have reinforced concrete or pre-stressed concrete. Reinforced concrete will have rebars, fibers, ferrocement. Pre-stressed concrete will have pre-tension, post-tension, bonded, unbonded. Material, similarly metal, steel, hot rolled, cold formed, aluminum, extruded, formed, plastics, wood, natural, laminated, and then many composites. These are all structural materials. So as you can see, it's a broad body of materials that you may need to deal with while making your structures. They can be very simple, they can be very complex. Simplest material is steel. One of the simplest materials to deal with is steel. Concrete is extremely complicated material, right? And then wood is also complicated, and composites are of course very complicated, right? And then you, of course, I did not mention here the carbon fibers and glass fibers. They are also non-structural materials. So in fact, they should also come here in non-metals here. So fiber, various types of fibers are also now becoming important structural materials. So this is another way of looking at the structural material that we will deal with. Concrete, and also plain, reinforced, pre-stressed, confined, unconfined, ferrocement. So there are many ways that you can organize materials depending upon what you are going to do with that. Now let's come to what kind of material behavior we are going to need and what properties we are going to need. What do you think, what is the most important property of a material? Just now we already talked about it, stiffness, right? We are going to need stiffness for analysis. And for design, we are going to need strength. Two different things. For analysis, we are interested in stiffness because that is part of the, and for design, we are interested in strength because we want to control the response, we want to limit it. So limit is strength. So we are going to need these two very basic material properties somehow. They seem very simple, but as we will see, they are not. Of course, on a very basic level, Hooke's law states that within the elastic limit, the stress is proportional to strain. So modulus of elasticity is equal to stress over strain, and that is the stiffness, right? Same relationship between force and deformation. So if stress is force, strain is deformation, it is the same relationship of the stiffness. So we can calculate the modulus of elasticity like stress over strain. And it should be very easy, right? This is valid only for limited cases, but unfortunately, this is only valid for very limited cases. So if you have been thinking about modulus of elasticity as a constant, it is not true. It isn't a constant. And it is only useful on a very limited cases. There are many stress and strain components and many properties. And let's go into that part now, right? So this is good, but this is not enough. First problem is this. This is a material block, small block of material. And that small block of material can have strain in any direction and corresponding stress in any direction. So that means the block, if you stress it this way, on that small area, you will have a strain. Axial stress, axial strain. In that direction, axial stress, axial strain in this direction, axial stress, axial strain in that direction. So axial, at least three axial strains and axial stresses are possible, correct? In each direction that you pull the material. Correspondingly, 3 strains will be possible, right? Shear strains. So, which means that this simple material has 6 components that we need to deal with. 6 strain and 6 stress components. 3 axial, 3 shear, correspondingly. So right away, when we talk about E, what E are we talking about? Which stress over which strain? That means there must be 6E. There could be 6E for a material, for each direction. depending upon which strain you are dividing by which strain, which stress is dividing by which strain. Second problem is that these are not independent. They may not be independent. For example, if you press something in this direction, there may be strain in the other direction, perpendicular to that one, in which there is no load applied. And so though the idea that you put a stress on this one will produce strain, actually you applied this stress in this direction, but strain is on the perpendicular direction, right? So that means that will add to the strains in the other direction. Same is the case with shear. So that means the behavior of a material block is going to be quite complicated when subjected to more than one strains or more than one stresses. And they must be linked to each other somehow. So that means now we are going to need more properties. One E is not going to be enough. So we introduce two more properties here. One is called Poisson's ratio, right? Poisson's ratio. What is a Poisson's ratio? Correct. And what is the shear modulus? It is similar to E, but for shear deformations, right? So you're going to need now at least minimum of 3 properties for the material to define all of the behavior in this particular case. One is modulus of elasticity for each direction, E in each direction, and then G for each direction of shear plus Poisson's ratio, right? Also in each direction. So you need a lot of properties now for this small material block. In fact, 36 in all, 6 by 6, right? So which means it is a very, it's not as simple as we started. So this is only one problem, that we are not dealing with one stress and one strain component, we are dealing with many. So there is interaction. So the whole definition cannot be defined by one number. Many properties are needed just for that purpose. But this is only the beginning of the story. Second part of the story is this, that stress and strain do not have a relationship which is constant all the time. In fact, it is changing all the time. If you start from this point at 0 stress and 0 strain, and you start with a little bit strain, corresponding stress or stress and strain, after some time, the relationship between them will no longer be linear. The structure will start to deform faster. And then if you go to this point, it will also become flat. And if you unload it, if you unload the structure, it will not go back in the green line. It will follow another line. And if you load it, it will go another line, and it will go here. This is a typical behavior of structures. Structures do not go in a straight line, not linear, that we assume mostly. So relationship between force and deformation is not linear. It is only linear for a short time, short range. It is unlinear. Because if it was linear, it would be impossible for structure to collapse. Because according to the relationship F is equal to Ku, if you apply one small force, you have small deformation. You apply large force, large deformation. Let's say 1 ton, 1 centimeter deformation based on the stiffness. 2 ton, 2 centimeter, 100 ton, 100 centimeter, 1 million ton, 1 million centimeters. How can you have 1 million centimeter displacement in a structure which is only 3 meters? Impossible, right? So that means something must be wrong with that equation, and it is. That equation is not valid, because after some time structure will collapse. So that equation will not be valid, and in fact at the one time structure displacement will move faster than load. And at one time you do not increase the load, still deformation increase, and so on. So this is the real behavior of the structure, which means that the stiffness equation that we saw just now actually has no meaning, right? It only has meaning on a small range. After that, the K must change. Relationship may still be the same, but K will keep changing. So a single value of K cannot be used. And that K is changing because of the changing material, changing properties, many things. Very, very, and most importantly, it also depends upon where you are, how have you come here? So as you can see from here, initial stiffness, first yield, strain hardening, ultimate strength, ductile limit, strength loss, many things will happen along the load deformation of a structure. So we must be able to predict this. Basic properties then that we need are, for analysis, modulus of elasticity, we just now mentioned. The only change we will do is modulus of elasticity at different levels of loading, or different levels of strain, because it's not a constant. Poisson's ratio, shear modulus, thermal expansion coefficient, alpha. Also you need, because temperature, when you apply temperature to material, it expands, right? It not only expands, its material behavior also changes. We will talk about that in a minute. For design, we need something like yield stress, yield strain, failure strain, these kind of things. So we need failure criteria, and we need stiffness properties for analysis, and we need failure criteria for design, both of which need to be defined to be able to complete the analysis and design process for a structure. And that is what we are going to. And the curve that I showed you before, if you go there, in fact, it defines most of these things here. So this curve defines failure, yielding, residual strength, stiffness at various locations. So if we are able to generate this curve, we will be able to get most of those properties from that curve, right? All right. On top of that, there are some other properties which you also may need sometimes. Relaxation. What is relaxation? Relaxation is basically change of the stress without change of strain. Same thing, but stress changes. The material becomes relaxed. If you put something in long, first of all it is in tension trying to, and then after that it just becomes relaxed. So it's relaxation. So it happens with steel. Similar things happens with concrete called creep, which is opposite of kind of relaxation. This happens under compression, right? If you compress concrete, it starts to creep, right? So that is another. And shrinkage, similar to that one. Shrinkage happens just because of nothing. No force, just strain changes by itself, right? So these, and fatigue, repeated loading and unloading creates another phenomenon. And confinement-based changed properties. So properties change if you confine the material. That means the effect of the volumetric or other strains on this one strain. So those kind of things. We will talk about a lot about confinement later. So these are things on top of the basic properties. That means materials are really complex. And that's what I said. Modeling of the materials correctly is a very complicated, complex process. And most of the time, people are spending a lot of time trying to understand materials. Most of the research these days is on material modeling. And there are some materials that we didn't talk about. One of the most complex one is masonry that we didn't even talk about. That's another level of complexity. Masonry, unreinforced masonry, is one of the most difficult materials to deal with right now. So, the properties of the material actually depend on a lot of things. First of all, basic material composition. What type of material that is. Of course, that is important, plastic or concrete or steel. So that will govern how the material is going to behave in different directions. Initial conditions. When you started, what was the condition of the material? For example, when they make steel and they heat it and cool it during the process, it produces some initial stresses, locked-in stresses in the material and strength. And that already changes before even you start to load it. So initial conditions. State of strain. Where are we now on the strain level? The properties will depend on the level of strain. Direction of strain. Which direction? How many directions strain is applied? History of strain. How many times have we applied the strain? Right? Where did it come from? it's not the current strain which is important, it's also important how we came here. Where did we come from? So past of the strain is also important. Time since initial strain. When did the strain first time started? How long ago? Because creep and relaxation will depend on time. Temperature. What is the temperature at this time? And what is the temperature when the material started? When the materials become heated, they change properties. Cyclic strain. How many cycles have gone through before we are talking about this strain? Rate of strain change, velocity and acceleration, damping properties. So you can see properties of the material depend on so many factors. Modulus of plasticity changes because of each one of them. Different temperature, different E. Right? Different level of strain, different E. So on and so forth. So the material properties, the basic material properties that we talk about, they all depend on so many factors. So if we are not able to understand and incorporate all of these factors, that means we will not be able to predict the behavior of the real structure. So material behavior depends on, as I mentioned, many things, and let's take a look at some of them, important ones. First one is linear, nonlinear. Response can be linear, nonlinear. What does it mean, linear, nonlinear? Also, elastic, plastic, inelastic, hysteretic. These terms are used quite a lot. So let's try to understand these, right? Linear. First thing, linear. What does it mean, linear? Linear means that we have a strain and stress. The relationship between them follows a line. No matter what is the level of strain, no matter what is the level of stress, and it is infinite, goes on forever. So you load, you increase the strain, stress increases, or you increase the stress, strain increases, and if you unload, they go back to zero. That is the normal expectation that we have been using in our simplified assumption that stress and strain are linear and they can go up and down forever and go on forever, right? Of course, not true, but that is the basis of most of our elastic analysis and design, linear elastic analysis and design. Okay, so this is the minimal level of our understanding. Second is linear inelastic. What does that mean? That means this, that you load it, it follows the linear relationship, but when you unload it, it also follows a linear relationship but goes to another point. It does not come to the origin. So this is the inelastic part of the strain. That means strain accumulates, damage accumulates. So every time you load and unload, there will be some strain which will not go back. That is called damage. So that means the material is damaging. Next time, more strain. So after a few cycles, it will break. That's what we normally do. We want to break something, we take it, we twist it, tick, 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 tick. After 5, 6, 10, 15 cycles, it breaks. Right? It's fatigue, also this behavior combined together. So we use that in our normal work. Next one is nonlinear elastic. Nonlinear but elastic. That means the relationship between stress and strain is not straight, but it still comes back to the origin. Like that. So of course, rubber, elastic. You stretch it a lot, but leave it, it comes back there, even though the extension is not linear. Right? So many materials are like that. They're very good at behaving in that way. And these do not exhibit any damage. So these materials you normally cannot break by twisting. That's why rubber you cannot break by twisting. Right? And then comes the worst of them all, nonlinear inelastic. Which means it goes in a nonlinear way, it comes back in a nonlinear way, maybe this way or this way. We don't know. Could be any way. And this is the worst material, most complicated, and reinforced concrete is one of them. So reinforced concrete is a non-linear, inelastic material. Right? Steel, most of the time, is linear elastic to a certain level, or could be linear inelastic. but concrete is nonlinear and inelastic. So that means we are dealing with 4 basic types of material behavior, right? Linear, elastic, linear, inelastic, nonlinear, elastic, and nonlinear, inelastic. So if a structure is made up of these materials, they automatically will behave in this manner. So if you make a material, make a structure from such materials, because material behavior is the starting point, so it will be exhibited in the structure also, right? But it is quite possible that the material you start with is linear elastic, but the structure is nonlinear inelastic, because other components of the stiffness will come into play, right? So important to remember that if the material has a certain behavior, at least that will go forward, but other parts may modify it as we go down, right? For example, the material that you start may have a linear elastic properties, but the cross section is cracking. The cross section is changing dimensions, right? So that means the next level will not be linear, it will become non-linear, right? So there could be many combinations of the cumulative effect. Normally, this is how we represent many materials. Most of the real materials can be simplified into this shape. Linear, perfectly plastic, bilinear materials, represented by 2 lines. So one portion for the linear range and one portion for the non-linear range. Just make it like that, simplified. And this is very good, because it makes the calculations very easy. So a lot of materials, even though they are not like this, they can be simplified to be bilinear. Elastic, perfectly plastic, right? They become linear, and after one point suddenly become plastic. That means they just keep on going. Plastic means the strain keeps on increasing at the same stress level, like a plastic flow, which just flows, right? But a lot of materials, like concrete, have behavior like this. They go and then come down in that way. So this is the elastic plastic material, but not perfectly plastic. Not elastoplastic, but elastic plastic. They become, and they have a, so typically concrete is represented by this graph, and steel is represented by the previous graph. Both of them incorrect, but assumptions, good enough, right? But we will try to go beyond that, of course. So this is how basically every material can be classified into one of these 5 types, right? So that means for getting the material properties, if we can get the stress strain curve, we can determine most of the things that we want. And if we do a cyclic test, then we can also determine other properties that we need, right? But the problem is it must be done at different temperatures. You know, the other things are still there, time dependent, other things still cannot be done. So the basic properties can be determined from the stress strain curve. That means take the material, put it in the lab, and test it until failure, right? And plot the points along the way. Ductile and brittle. That is also very important to understand. Ductile material or behavior is the deformation and force, it goes on for a while before it breaks somewhere. And brittle is it goes and then suddenly it breaks, right? And this is called ductility. The length of this curve from here to here, we will talk about more about it, is called ductility. So very small ductility, no ductility, and large ductility. So we need to deal with materials which are brittle and ductile in a different manner. We treat them differently. Rules are different for these 2 materials, right? The design rules are different. The expectations are different. So we prefer this, we don't like this, of course. And we try to convert brittle materials into ductile materials. So coming back to this stress strain curve that I just showed you is not one. It will be in each direction we will have similar curves, right? That means that curve, that property is not the end of the story, because that is only one direction. Every direction could have a different curve, different relationship between stress and strain in that direction. Some brittle, some not brittle. Same material, in certain direction it will be brittle, some direction it will not be brittle. Some direction it will be cyclic very good, some direction it will be not good. So same material can exhibit linear, inelastic, nonlinear properties within that material depending upon the direction of loading, right? So that makes it even more difficult now to model and to predict how the material will behave. And not only that, the material in one direction will be affected by the strains in the other direction. So material which was ductile may become brittle because of a loading, and material which was brittle may become ductile because of the other loading. So that's how we can change concrete to be a ductile material, by looking at the stresses in the other direction, not in the direction that we are talking about, right? So this equation, this matrix, this relationship can then make the things more interesting as well as complicated. So that is the matrix which relates the stresses and strains. And that leads to these three types of materials: isotropic, orthotropic, and anisotropic. So these are the three types of behavior of the material which link the directional properties with each other. Isotropic is a material which has the same behavior in all directions, independent. So whether you pull it in this direction or that direction, it has the same behavior, right? That is isotropic. And each material, each behavior is independent of the material behavior in the other direction, right? Most materials are not isotropic, but we consider them isotropic. For example, beam, concrete beam, we assume that because it's only going to bend in this direction, we consider the beam, reinforced concrete, to be isotropic in this direction, because there is no loading on the other direction, only one directional column, one directional loading. So we can consider it isotropic at that time, because the other direction loading is not possible, even though it is not isotropic. So we consider that. Second is orthotropic. Two direction behavior is different, but independent. Like for example, concrete slab. If you have reinforcement in two direction and the two direction reinforcement is different, bending moment and stress and strain in the two direction will be different, but they're independent, right? So orthotropic. And steel deck, if you have it like that, one direction no stiffness, other direction lot of stiffness. Precast slabs, same case. So there are many structural members for which the material becomes orthotropic because of the way the material is made. Wood, for example, one direction very strong along the fiber, across the fiber not so strong. So wood becomes orthotropic. But behavior is uncoupled. The last one is the complicated one, is anisotropic. Different behavior in three direction and behavior is coupled. That means each direction the behavior is different, and also it depends on the behavior in the direction. So it's coupled. And that is how many materials are actually that way. But we simplify them to be either that or that or that, depending upon how we use them. So a real solid of material, the real block of material, is going to be of this kind because of the Poisson's ratio. They are going to be linked to each other. Soil, for example, is highly anisotropic. It depends on how three-directional loading is important, even concrete. But we don't consider them like that. So normally you have been dealing with isotropic materials so far, or knowingly or not knowingly. You have been assuming that materials are isotropic. They have only behavior in one direction, not influenced by other things. simplification, take a beam section, as we mentioned to you last time. One cross section, one axis. So that equation can be simplified to be this equation. That matrix can be simplified to be this equation because we eliminate all of the things from that. We consider it isotropic, we remove all the coupling between shear and that. When we remove all of that, we end up with the same relationship. So basically this relationship, stress over strain, is a simplification of the big matrix, right? This is only a special case of the full 6 by 6 matrix relationship between stress and strain by putting certain things to be 0, right? Because it's a certain, we are simplifying it for a certain loading case. So the point being that this same big matrix contains all of the behavior, and we can simplify it for a particular application by setting the values appropriately to 0, depending upon what we are doing. Clear? When we talk about slabs, we will not have this, we will also have other relations linking them. So here G and E are independently defined by replacing G by that equation, in that equation, so we can simplify that. Alright, so just to give you a clear idea that this equation came from the big behavior by a simple case. Does not mean that this is true all the time. Let's go back to that stiffness, structure stiffness, one more time after this new knowledge. New knowledge is that the stiffness of material is not a constant. It is represented by a stress strain curve or a graph. Also, the section stiffness is not a constant. It is also represented by its own graph. Member stiffness is also not a constant. It is also represented by its own graph called P delta effect. Many things. You know, every level has its own non-linearity or complexity added to the behavior, to the stiffness behavior, until we get to the total structure stiffness, which is a plot between deformation and force. This is a plot between rotation and moment, curvature and moment, strain and stress. So at different level, the name changes. First of all, stress strain becomes moment curvature, becomes rotation, moment rotation, becomes deformation. So it keeps on changing the level, but the meaning is the same. And it becomes a summation of the previous history, or previous properties, right? So you can see from here that if you start with a nonlinear stress strain curve, the structure must be nonlinear. You may start with a linear stress strain curve, but if this is nonlinear, the structure will become nonlinear, right? The only way for the structure to be linear is that at every step that we have linear behavior, right? Otherwise, any one of them can make the structure nonlinear. And this is something that almost all engineers working in the field, not dealing with complicated stuff, they assume their structure to be linear elastic, which is definitely not true. But we have no choice at some times. We just simplify it to be like that. All right, so now we know that to make the total structure stiffness, we must understand the material stiffness behavior, material behavior clearly, right? And then next one will come cross-section behavior. Next one will come member behavior. So we will try to cover step by step. Material first, then cross-sections, then members. Now, I'm going to show you some forms from ETABS. Yes? Or actually not ETABS, this is SAP 2000. I took the screen captures of the data input forms in SAP to define one material, right? And you will be surprised how many forms they have just to define one material if you want to define everything that we talked about. Starting point, you need to define modulus of elasticity, mu, and g, and alpha, basic properties on this side, and then some other properties, and then come these 4 buttons, which talk about nonlinear properties, which talk about time-dependent properties, which talk about the velocity-dependent properties, which talk about temperature-dependent properties. So when you start going into each one of those, it starts to keep expanding. Then it talks about anisotropic material, it talks about the orthotropic material. So really speaking, there are about 16, 17 forms, big ones, which need to be filled up before you can define one material completely for the analysis if you want to do a sophisticated analysis. If not, you can just give modulus of elasticity E and you're done, right? So the difference between simple material and full definition of material is huge. One value against hundreds of value, right? So I'll just show you, just for you to get an idea why we need to study all of this, because actually it is needed in the analysis. If you want to do sophisticated or complete analysis, this information will be needed. Then you go into orthotropic properties. If you want to define orthotropic material, then you go to anisotropic properties. You need to define so many E, so many values, not one, because every direction is different, right? So many G, so many, not one. So you can define anisotropic properties, uniaxial properties, which is different from, which is similar to isotropic but completely uniaxial. No other component is present. Confinement properties. If the concrete has transverse reinforcement, it will change the properties of the axial direction because of the confinement, and you define the confinement parameters, and there are many forms for the confinement. We will deal with confinement separately. Nonlinear data, you have a lot of other nonlinear data to be added. You have damping properties related to the velocity and the energy dissipation, and you have the time-dependent properties. Over time, 10 years from now, what will be the property? 4 years from now, what will be the property? Right? So you can see that there are literally hundreds of properties to be defined for a material to know exactly how the material will behave. And still, SAP is not so good in modeling behavior. If you use programs like ANSYS or Diana or other programs of that kind, you need even much more than that, right? So, which means that modeling and understanding of materials is critical to the analysis and advanced analysis especially, to understand the structure, to be able to predict the response more reliably. And many of you will be doing thesis on such topics using ANSYS or Diana or other program, because SAP will not be enough for you, you will realize, for your research, right? So we will have to come and visit these properties again. Any questions so far? Let's stop here. It's a lot of information today. Yeah.